Now that we have our definitions, let's try to apply them. Parts from a supplier are shipped to a purchasing company in lots. Upon receiving a lot of 1,000 widgets, the purchaser examines a sample of 20 widgets to check on the number of defects, if any. The contract between the purchaser and supplier states the procedure for determining the acceptability of a lot. Widgets are just items. We could be talking about bolts or gears or some other manufactured product. And we have a supplier shipping to a company in a big group. And the purchaser examines not all of them, but some of them to see if they have any defects. It'll take too long to examine all 1,000 of them, so they take a small sample and examine them. And then there's some information that we don't know, but that's okay, that will determine if the purchasing company will accept that lot or they're going to send the whole box back because there are too many defects in the sample. Okay, what is the population that we are studying? What is the population that we're interested in? Consider you as the purchasing company. What are you receiving? You're receiving the lot of 1,000 widgets. And then you're examining a sample of 20 widgets. That sample is a key word in here. The population is the 1,000 widgets that we receive. And the sample will be the 20 widgets that we examine. What is the variable that we're interested in? What makes the sample special? What are we looking for in the sample? What is it that we're trying to determine? We're trying to determine the number of defects. Or we're trying to determine if there are defects in the widgets at all. So we could just say defects. Whether the widget has a defect or not. That's our variable. Again, I know it's a little weird when you're coming out of algebra talking about letter variables, coming into statistics talking about characteristic variables, but that's one of the many ways that statistics and algebra are very different. Good job. Let's try another one. Boston medical professionals wanted to investigate the level of knowledge of colds in their community. They surveyed 211 people. 60% of the people were aware that colds are caused by viruses, but only 40% knew that antibiotics could not cure a cold. So what is the population and the sample? Remember that the sample is the smaller group from the bigger one. And the sample is usually what we collect the data on. We collected data on 211 people. That's our sample. But where did those people come from? Those people came from the Boston community. The Boston medical professionals are wanting to investigate the knowledge of colds in their community. So the population would be the community of Boston. Larger group, population. Smaller group, the sample. Is the value 40% referring to the population or the sample? Well, let's go back to the problem. They surveyed 211 people. 60% of the people were aware that colds are caused by viruses, but only 40% knew that antibiotics could not cure a cold. This information refers to the people they surveyed. So the 40% is referring to the sample. Some more examples, again, applying these definitions. I want you to take a moment for these next 3 problems and see if you can answer them on your own. Pause the video, try it out, and when you resume, we'll walk through. I want you to pause and do number 3, resume, and we'll work through number 3, and then again we'll pause at 4 and work through 4, and pause again at 5 and work through 5. But again, try. The important thing is that you try this on your own. See what you already know with these definitions, what you can infer from the situations that are presented. and then correct mistakes that you make. Remember, mistakes are important to learning. And if we don't make mistakes, then we're not learning anything. We're just practicing things we already know. Hit that pause, try it on your own, and then come back and we'll talk through it. On the first day of statistics class, a professor conducted a brief survey asking students to rate their level of math anxiety. She determined that 26% of her class could be identified as possessing a high level of math anxiety, whereas 37% could be classified as having some math anxiety. The remainder of the class had either low or very low levels of math anxiety. What data was collected? The levels of math anxiety for each person in the class. What were the results of the data collection? This is an example of the descriptive statistics. So the results, she determined that 26% had high levels of math anxiety, 37% had some math anxiety, and the remainder, which if we do a little tiny bit of arithmetic, 100% minus 26% minus 37%, we can pull up our calculator. We get 37%. 37% had low or very low levels of math anxiety. That's our descriptive statistics. We've collected the data, the levels of math anxiety, and now we're summarizing it. Summarizing it with percentages, grouping the different data values together that are the same, and then giving a description of those. Was there variability in the data collected? Okay, this is a little tricky. This idea of variability means that, actually, I'll go back to eye color. Think about eye color. We could have light brown eyes, we could have medium brown eyes, and we could have really dark brown eyes. The word brown encompasses all of the different shades of brown eyes that we could have. So that is an example of variability in the data. In this situation with math anxiety, my perception of math anxiety may seem high to me, but that same level of anxiety that I feel, if someone else feels that same level, they may think it's some. Maybe they have other anxieties that they're fighting, or maybe they just don't feel like that level is high enough to be called high. I hope that makes sense. I hope this question starts to get you thinking deeper and more critically about the statistics that are presented to you on a daily basis. So there is variability in the data collected. And we can say one person's perception of high level of anxiety might be another's low level of anxiety. It's hard to tell because we're talking about opinions. What percentage of the class had low or very low levels of math anxiety? We found that earlier, that 37% when we did our descriptive statistics. And then the last question, what could not be determined from the percentages? This is a pretty open-ended question. There are lots of possibilities here. We don't know how many students are in the class. Percentages often obscure the real numbers. So we have to be really careful when we're presented with percentages, because percentages of small groups sound big when they might not be. With percentages, we don't know how many students were in the class. It seems like in here that everybody had at least a little bit of math anxiety. There was not a single student represented in the information that had no math anxiety. So we don't know if maybe the low or very low included no math anxiety. We don't know how old they are. There's nothing in here that tells us their age. We don't know what math class they had before. And all of these things could be asked. We could find out just by asking, expanding this question that the teacher asked. What else are we missing? Expand your thoughts on just this little scenario. What else might we be interested in? Maybe how long ago their last math class was. Maybe what kind of anxiety. For those of you who attended my Conquering Math Anxiety Smart Shop, you learned there are 3 types of math anxiety. If you haven't attended it yet, there's still some more that you can check out. Just go to that Smart Shop webpage, look at the calendar, or see if one fits in your calendar, and go attend it. Other environmental causes of anxiety. Math is not the only reason you can have anxiety. How they might try to alleviate the anxiety. So we might be interested in, what do you do to try to help your own anxiety, and see if maybe that helps other students. What else? What other things might we want to know? What other information is left out from just collecting these percentages of levels of anxiety? If you think of others, put those down too. All right, now moving on to number 4. Again, hit that pause, try the questions on your own. When you resume, we'll talk through it together. In a recent election, 600 potential voters of a congressional district were polled to discover whom they plan to vote for in an upcoming election. The results indicated that 314 voters, or 52% of the sample, planned to vote for candidate Smith. 239 voters, or 40%, planned to vote for candidate Doe, and 47 voters, or 8%, said they did not plan to vote or had no preference. Based on the results of the poll, the researchers estimated that candidate Smith would win the election with about 52% of the vote. And the first question, why are descriptive statistics necessary to summarize the results? Well, when we're looking at 600 voters to poll, the data would be who they're voting for. So we would have a listing of whether they were voting for candidate Smith, candidate Doe, or no preference, and we would just have all of these listed out. That's not easy to understand when you're looking at data. So the descriptive statistics, the percentages give us a concise representation of the data set, so it's easier to make sense of it. It makes it a little easier to understand. What generalizations were made, or what inferences were made, what conclusions were made in this situation. The conclusions that were made, there's only one. Candidate Smith would win the election with about 52% of the vote. And we're assuming the 600 voters are a good representation of the population. The generalization was that Smith wins with 52% of the vote. Now, I make this first statement up here, and we haven't really talked about what samples make good representations of the population, because that's in section 1.3. Not all samples are good representations of a population. We have to take the samples in a good way and in a random way in order to call it a good sample. We'll expand more on that in section 1.3. So this is an example of inferential statistics. We take a poll, we get some information, and then we make a conclusion, a future prediction. Candidate Smith's going to win the election with this percentage of the vote. Granted, 52%, it could go a little bit more or a little bit less, but that's the conclusion that they made. So what would make you trust the results of the poll? For me, what would make me trust the results of the poll is if a reliable, unbiased source or a company known for good statistical sampling techniques ran the poll. What would make me distrust the results of the poll? If a news network ran it. Any of them. Most, not all of them, but most of the news networks that conduct polls are doing something called a voluntary response sample. And again, we'll get into this in 1.3, but in a nutshell, a voluntary response sample means you choose whether you want to participate or not. So usually they'll put something on their website, a quick little poll. All of these polls that show up in social media are voluntary response samples. So you have to be really careful with these because they are not good representations of the data. And I would not trust the results if Candidate Smith did it. Because Candidate Smith, if he did it and his people are saying he's going to win, that makes me not want to trust the poll at all. He's sponsoring it. All right, let's try the last example. This one's shorter. Again, pause, answer the questions on your own, and then resume and we'll do it together. Many people believe in paranormal phenomena such as precognition, extrasensory perception, and psychokinesis. Is the extent to such belief in phenomena related to the type of high school courses taken by such individuals? A study in 1984 measured the belief in paranormal phenomena of 193 11th grade high school students. They also recorded the total number of science courses each student had taken. When relating the number of science courses to belief in paranormal phenomena, they discovered an inverse relationship. That is, the more science courses a student had taken, the weaker the belief in paranormal phenomena. First question, what are the two variables used in the study? So what two pieces of information did the study obtain from those high school students? They measured the belief in paranormal phenomena, and they also recorded the total number of science courses. So here we have two variables that we're collecting, the belief in paranormal activity and the number of science courses. And this is an example of inferential statistics that is also called correlational statistics. Correlation. When we talk about correlational statistics, we're looking at two variables, or possibly more, but we're going to focus on two variables in our class. Why would it be important to study correlational statistics? Well, we can see if two variables have some relationship between each other. And that relationship might inform experiments to determine a cause and effect, or remedies or changes that we could do. But we do have to be really careful with correlational statistics because just because there exists a relationship between two variables, that does not mean that one variable is causing the other to happen. So a correlation does not automatically give us a cause and effect situation. We just have a relationship between them. The only way to really determine a cause and an effect is if we run an experiment. And we'll be talking about experiments and observational studies very soon. So we can see whether two variables have a relationship. The relationship between two variables may help inform experiments. It may help determine some remedies or changes or improvements that might need to happen. But just because there is a relation between two variables, in some situations that may mean it's coincidental. So we're going to explore this idea of correlational statistics in this chapter, but also in chapter 10. Correlation and regression comes for us in chapter 10. So we'll visit it in this chapter talking about some misuses of statistics, and we'll also visit it in chapter 10 when we actually dive in and explore what it means to find a correlation, how we can find a correlation between two variables, and what we do with that.